Okay, everyone, we're back for part three of our first section on series. So we've introduced what a series is and our basic approach. And then in the last video, we got into the geometric series test. So we just ended that last example right here. Now we're going to look at the next type of series test that we can apply. This next one could apply to lots of different things. And it's a really simple test, comes in really handy, and it's based on some cool logic. So we're going to start with this theorem you see right there. If a series converges, and you notice that it starts at n equals 1, that's kind of the default. It could start anywhere. Any infinite series, if it converges, then the limit as n approaches infinity for that nth term describing the sequence, that limit must equal 0. Okay, so maybe let's pause. If we were in class, I would say, hey, I would just write that on the board and say, think about that, just based on your intuition, do you agree? So we can't really do that now, but it must follow. What's going on is if a series converges, that means as I add up all infinitely many terms, they have to level off to a particular value, right? So that means each each term in the sequence as it gets bigger and bigger, that's got to be getting smaller and smaller and smaller, so that as I keep adding them up, it's leveling off to a single value. Okay, that'd be true back in geometric. Like we said, this one back here converges. Well, every next term is smaller than the one prior, right? As we keep increasing the exponent, the terms get smaller. And that just has to be true in general. For any series to converge, the terms have to be getting smaller and smaller and smaller. Now, they could be negative or positive, but just so long as they're getting smaller. So the limit of that sequence describing the terms has to go to 0. Okay, hopefully that makes sense, or else none of the rest of this is going to follow. Here's how we're going to work. So here's the logic. Think of this statement, this theorem, as an if A, then B. If it converges, then the limit equals 0. Okay, if A, then B. And here's what we're going to do. We're going to switch it up. And in logic, if you've taken a logic course or if you might take one in the future, what we're going to do is called the contrapositive. So we're going to reverse the order and throw some negatives on there. If A then B, if that's true, then this must be true as well. If not B, then not A. If B never happened, then we can say for sure that A never happened as well, right? If A happens, then B follows. So if B never happened, then A must never have happened either. Okay, for any if-then statement, if A then B, the contrapositive always fits. It always follows as well. There are other types of statements that would not always follow. Like if I said, if not A, then not B, that isn't not always true. But if this never happened, then that we know for sure that this did not happen either. Because if it did happen, then that would have happened. But okay, enough said. So let's take the contrapositive of our theorem, and that'll be a new theorem. Actually, we're going to call it by a new test. The divergence test officially. Sometimes you hear it called the nth term test. Anyway, here's what it says. If not B, so if not this, if that limit does not equal 0, then not this. Well, if the series does not converge, then we'll just say then the series diverges. So if the limit does not go to 0, then the series diverges. If those terms are not getting smaller, then we know for certain when we add all them up, it's either going to be infinity or negative infinity. Okay, now this is a very powerful test if it works. If we can show this is not equal 0, oh my gosh, boom, we're done. It diverges. Let's take a look. I've only got 2 of these for us. I think that'll be plenty for now. Okay, so let's take a look at this one. The sum from n equals 1 to infinity for this fraction, 3n over 2n plus 1. You think, okay, well, it's definitely not a geometric series, right? So maybe our new test will work. Let's take the limit as n approaches infinity for 3n over 2n plus 1. We notice that would be infinity over infinity. So we need to use L'Hopital. At this point, I remember that we actually did L'Hopital back in this class. You might not have to think all the way back to Calc 1. We did it with improper integrals. Anyway, infinity over infinity, let's apply L'Hopital 3 over 2. Well, the limit is going to be 3 over 2. Well, 3 over 2 is not equal to 0. We showed the limit is something not 0. So we are done. Our series, our original series there, diverges by the divergence test. As n gets bigger, the terms in the sequence get larger. So we're always adding something, bigger and bigger. It's going to add up to infinity. It diverges by the divergence test. And what a quick, easy way to check. That's pretty cool. Okay. Let's try another one. Part E, does it converge or diverge, right? Same question. Let's go with this one. N equals 1 to infinity, 2 over 5 to the n. Well, let's see. Hey, maybe I can find the answer by the divergence test. So I'm going to take the limit as n approaches infinity for my nth term. But in this case, that means my denominator is getting bigger, so the whole thing is headed towards 0. Oh my goodness, hey, if I take the limit and I get it to equal 0, can I claim something? Now this is a very delicate part of the logic. If my limit of my nth term in the sequence equals 0, I cannot say anything. I don't know if it converges or if it diverges. If my limit does not equal 0, I know it diverges. Boom. But if it does equal 0, I have no clue. Now, people like to think that they have an answer, but let's go back to the divergence test. If it doesn't equal 0, I know that. But if it does equal 0, this prior theorem does not work backwards. If it converges, then I know that follows. But if that happens, I have no idea. It might still diverge. Okay, so at this point, again, I know that the logic is kind of delicate, and maybe some of you guys are like, no, but it has to converge. It would have to converge. We're going to see examples. I don't think it's not in this section, but in the next one where things are not what they seem. So let's just say at this point, we have no idea. The divergence test is inconclusive, doesn't give us an answer yet. Well, is there another way? And it turns out, well, there's only one other test that we're aware of, right? The geometric series test. Well, wouldn't that fit the geometric series? Okay, so maybe focus right here. 2 over 5 to the n. I'm going to write that as 2 times 1/5 to the n. That would be this guy rewritten. Now there's a problem with that, it turns out. For a geometric series, I can't start at 1. I have to begin at n equals 0 if I'm going to use the test. So like, oh my goodness, what do we do? Okay, so we have to be kind of clever. We're going to turn that 1 into a 0, but then we're going to realize this has an extra term. This one has a 0 term where this original series that we're looking at does not. Well, what would that 0 term be? If you plugged in 0, that would be 2, right? So we're going to then subtract 2. Okay, my kind of arrow here is to the next step. All right, so as soon as we do that, now we've essentially added 2. So we're going to subtract 2 to balance it out. Subtract the 0th term is my note there. Add another term, but then just subtract whatever that number is. Okay, I'm going to move along. Hopefully you're keeping up with me. If not, that's why we have the live meetings in our normal class time in addition to the videos. I'm going to say, okay. So now I really do have a geometric series. It starts at 0, it takes the form, then I'm subtracting this. Well, I know that this converges. I know my r is less than 1. So let's find out what it adds up to. 2 over 1 minus 1/5. I'm still subtracting the 2. This first part would work out to be 5 over 2. I subtract the 2, I get a half. And so I know that this thing converges. Really, I knew that it converged way back here because that converges. And if I subtract 2, well, then that's still going to converge. I just didn't know what the number was. So I went through these steps. And now I can tell that it converges to 1/2 by the geometric series test. Okay, so part of the point of this example was to show you when the divergence test fails. When is it inconclusive? If my limit is 0, equals 0, I can't say a word. I just have to move on and do something else. And then there's this kind of delicate procedure of converting it from n equals 1 to n equals 0, and then applying my formula to get to what it actually is adding up to be. And there you go. All right, that's the end of this part. See you in the next one.